All right, so we are going to go ahead and do our second part of hypothesis testing today. So last week we did our first part. We're just going to go a little bit more in depth this week, talk a little bit more about the different parts of hypothesis testing. So first, just to compare again, to review, when we have a difference between confidence intervals and hypothesis tests, our confidence intervals are going to have our range of data. So remember, when we had our confidence intervals, we had a lower bound and an upper bound, and that's where it became a range. So remember, we had our lower bound, comma, upper bound, and then we were saying that we're confident that it is between these two numbers. We have a certain percent confidence. And then hypothesis testing, that we only have one single conclusion, which is the main difference there. There's not a range of data, so we're basically making a test and then saying, do we think something is going on there? So that's the main difference there. Let's keep on going. So when we're talking about hypothesis testing too, we want to make sure that we talk about errors and also just understanding with errors the different issues that we can have when we are doing hypothesis testing here. So when we're doing errors, our one example here is that we can either have a type 1 or a type 2 error. So in this case, our type 1 error is going to be when we reject that null hypothesis when our null hypothesis is actually true. So we are going to remember, you assume always that our null is true. That's the main thing to remember. And then also, in this case, we want to make sure that, so then with the type 1 error, since we're rejecting the null one is actually true, that's basically saying that we said that we found something significant when in reality, it wasn't significant at all. So we often set our alpha level, remember that was our significance level, we often set that at 0.05, so for 5%. So in this case here, remember our alpha level, which is also our significance level, it is our probability of making a type 1 error. So yeah, so remember, we assume null is true, so type 1 error is rejecting our null when the null is actually true. So that would be saying that there's a change when actually there is no change. And then that's different from a type 2 error, where we're going to fail to reject that null when actually the null is false. We denote that by beta. So type 1 error is alpha, type 2 error is beta. So for a type 2 error, we're going to fail to reject the null, so we're saying that there is no change when in reality there's some sort of change. The null is false, so that means that we have a change here. And then on this table, basically it's just a two-way table discussing, what would happen if you made these different conclusions. So like these are going to be your decisions, and then this is what's actually true. So you can see here, so if I were to not reject the null, but the null was false, that would be me making a type 2 error, if we're just finding the intersection between these two. So you can read this in any way, basically. You can read it with, let's say, if you reject the null, and then the null is actually true, so we said that there's a change when there really isn't a change, that would be our type 1 error, which remember is also denoted by alpha. So those are just different errors that you could make in hypothesis testing that we want to look out for. And our power, all that is talking about the probability that we commit a type 1 error, or everything except for the probability that we commit a type 2 error. So remember, beta is our probability of committing a type 2 error. And then if we do 1 minus that, 1 minus beta, that's how we're going to get our power there. So remember, for our power, for a type 2 error, that's rejecting our null hypothesis, given that the null is actually true. So if we reject it and say that there's no change, and then if we fail to reject the null, say that there's no change when actually there is a change, that would be our beta, and that's our type 2 error. And if we do 1 minus that, that's how we're going to get our power. So yeah, so if you decrease the alpha, you're going to increase the beta. So there is an inverse relationship between alpha and beta. And keep in mind this is with a fixed sample size, because if you were to decrease alpha with a different sample size for beta, that would skew it and make it a little bit different, because remember, sample size does change our significance levels. That's something important to keep in mind, because we always want a larger sample size. So if we have a smaller one, we may have different categories here, different numbers. Okay, so p-values. Basically, p-values is going to be, it's talking about what chance we're going to have of getting the value that we thought we got, and then something more extreme than that. So we want this to be small in reality, because if it's small, that means that there's a small probability that what we got was just by chance. So in this case, if we look at this, our p-value is going to be compared to our level of significance. So remember, alpha is our probability of making a type 1 error. So our level of significance is alpha. We often use 5%, 0.05 for this. And then, so basically that is going to be what we're comparing our p-value to. So we want our p-value to be less than or equal to this significance level in order for it to be statistically significant. Because that's saying that there's a small probability that what we got was basically just by chance. So yeah, so we always want to keep this in mind. And then if we go here and discuss kind of what could happen though when we find statistically significant results. In this case, if you see something that's statistically significant and it's published, you do want to keep in mind that there could have been a bunch of studies done that you could have had a bunch of studies done, but then they're only publishing the ones that were statistically significant. They're not publishing all the ones that weren't. So in reality, there could have been a bunch that were not significant, and then there could only be a few that were statistically significant, but they're only going to report those. So that's the main idea about publication bias. So we just want to find out here that there's really no difference in the population. 5 studies. So if, for example, if there was no difference in the population, and then out of 100 studies, they found 5 statistically significant ones, but like 95 that weren't, they're only going to report those 5, which is true that they found 5 that were statistically significant, but what they're not reporting is the other 95 that weren't. So it's something that you want to keep in mind, that not everything is always what it seems. And then practical significance is basically just taking like whatever we got. So like if we're going to have something like we get statistical significance, we want to see actually, like, is this actually something that is practically significant? Is this something that is significant in real life? So for example, so basically we call this the magnitude of the difference, or our effect size, because basically saying, is this important or not? Is this we found it to be significant, but like, is it actually something that we can use in real life? That's the main idea there. That's a little bit different than statistical significance, because statistical significance is just a number. Practical is kind of looking at everything else and saying, like, is this realistic in this aspect? All right, so let's do some review questions. We have quite a few today, just so we can get some extra practice. And if you haven't already, go ahead, put your Penn State email into the chat box for me. That would be awesome. And so we're just going to go ahead through these reviews. If you haven't been here before, we're just going to go ahead and I'll read through the question. Then you can just go ahead and type your answer into the chat box, and then we will go over it. So let's start this one. So hypothesis test for a population proportion of P is given below. So we have that our null hypothesis is that P equals 0.1, and our alternative is that P is not equal to 0.1. So go ahead and decide that if we have a sample statistic of n equals 100 and a sample proportion of p hat equaling 0.1, then what is our z-test statistic? So go ahead and try to solve this one, and then we will review it together. Okay, good job, guys. So yeah, let's go over this one. So if we were to look at this one visually, if we were to do it like conceptually here, and I were to draw it. So remember, when we're finding a z-test statistic, we're standardizing whatever data we already have. So if I were to take what we have originally in a normal curve and use the data that we have here, so our mean here is going to be whatever is in our null and alternative hypotheses. So that's going to be 0.1. And then what we want to do is standardize this onto a normal curve of our z-test statistic. So in this case, we're going to take this, and this will be our z-curve. And remember, our mean is going to be 0, and our standard deviation is going to be 1. Okay? So in this case, what we want to do is take this curve and standardize it and fit it onto this curve. So we're trying to find, where does 0.1 fit into this z-curve down here? So visually, we can decide that our answer would be B, because 0.1 is our mean of our original curve, and that aligns straight down with our mean of 0 on our z-curve, because 0.1 is 0 standard deviations away from our mean, because it is our mean. And then our our mean of our normal z-curve is also going to be 0 here on our z-curve. So that's why we can translate it to 0. You can also use the equation to find a z-score, which we will do up here. So if you're just looking to see how to find a z-score, remember that's going to be our p hat minus our null p, and then divided by this. So the square root of our null times 1 minus our null, and then divided by our sample size. Okay, so this is the equation that we can use to get our z-score. So if I were to actually do this, our p hat, we're given down here, is 0.1. So we're going to have 0.1 minus our null. So remember, I said that this is our null. Whatever is listed in our null and alternative hypothesis is going to be our null proportion. So that's also 0.1. So in this case, you really could just stop here and realize, because this is going to equal 0, and 0 divided by anything is going to be 0. So your z is automatically going to end up being 0. But you could plug in everything down here. You could go ahead and plug in 0.1 times 1 minus 0.1, and then divide it by n, which is 100. But doesn't really matter what this is, because it would come out to 0 in the end. So this equation is just another way that you can go ahead through and find your z-score in this aspect by just plugging in these numbers. But this is just a more conceptual way to understand that our 0.1 also aligns with our mean of 0 here, because our p hat was also 0.1. So that's why our z-score is going to be 0. Does that make sense how I explained that? Yep, yeah, it's definitely tough. So yeah, if you remember, so for C is just our p hat, so that's going to be the value we have on our original curve. But we want to standardize it and put it onto our z curve, so it's going to correlate with a z value or a z score of 0 coming from our original curve of 0.1. So, all right, good job, guys. Let's do some more. Okay. All right, so well, this is just the equation I just used to find our z-score. Okay, all right, so given that the alternative hypothesis is really true, the probability that the null hypothesis will be rejected is known as what? Let's go ahead and try to answer this one, and we will go over it then. All right, great job. So definitely our answer here is going to be A, because basically, I mean, this one doesn't require too much explanation because this is our definition of power. So remember, our power, if we were to write it actually out, it's going to be 1 minus beta. And then remember that our beta is equal to our type 2 error. So yeah, this is basically just our definition of what power is. So, you know, given that our alternative hypothesis is true, and so we could also write it like this, so this makes more sense. So probability that the null is rejected given that our alternative is true. So if you remember from our probability unit, that's where we get this from. So this is another way to write the definition of power. So our answer would be A in this case. So good job. All right. Oops. I just clicked something weird. Okay. All right, number 3. So let's see. So at one student-run cafe, the number of muffins sold each day was recorded for 47 days. Assume that this is a representative sample. So given the output, which of the following conclusions is correct? So go ahead and read through these answers and let me know what you think.
Quần áo mình có định cho vào thì cho vào nào. Có con đang ấy con đang làm này nên là con tôi cho vào nhá, nên sao để con làm.
All right, great job, guys. So if we were to look at this, if we look at this mini tab output over here, we have our p-value here, and you know we always assume here that if we're not given our alpha level, we're just going to assume that's 0.05, 5%. So remember, this is 5% chance of making a type 1 error. Okay, so in this case, if we were to go ahead and look at our p-value here is 0.1148, which is going to be greater than our alpha level. So if we do 0.1148, that's greater than our alpha, which is 0.05. So in this case, that means that we're going to fail to reject the null. So if we're failing to reject the null, we're saying that we still are assuming that there's no change. So if we're assuming that there's no change, that means that we don't have any evidence that there's some sort of difference going on here. So remember also that when we make a decision based upon a hypothesis test, same with confidence intervals when we did that too, we're always making an assumption based upon the sample. Or I'm sorry, based upon the population, never the sample, okay? So this is something to keep in mind. So that's why A isn't correct. A is stating basically the same thing, except that it's not talking about the sample. So A can't be correct because we're talking about the population. That's why our answer is D, because we're saying that there's not evidence that the population, because remember, our null hypothesis is always going to be talking about our population. That's why we're using mu, because this is talking about the population mean. That's the symbol that we use for that. B isn't correct because that just doesn't make any sense. This is, our p-value is not defined by what this says, so that's not correct. And then C is saying the opposite of D, basically. It's saying that we do have evidence, and this would only be correct if our p-value was less than or equal to alpha, which it's not, so C is not correct. So our answer would be D, because since our p-value was greater than or equal to alpha, we don't have evidence that our population mean number of muffins is greater than 5. So we're still going to assume that this null hypothesis that our mean equals 5 is still true, and that there's no change from this original question. Does this make sense to everybody how we solved that one? Yay! All right, awesome. All right, let's do a few more. All right, so a university administrator writes a report in which he states that at least 45% of all students have driven under the influence of drugs or alcohol. Boo, don't do that. Many others think that the correct percent is less than 0.45 or 45%. What are the appropriate null and alternative hypotheses in this situation? So go ahead and try to answer this one, and we will go over it. All right, awesome job. So yeah, our answer here is definitely C. So we can first of all rule out our A and B, because remember, we're always writing our null and alternative hypotheses in terms of our population, okay? Because remember, when we make a conclusion, it's always going to be about our population. So that's when the null and alternative are always going to be using P or mu. So it can't be P hat, so that's why A and B can't be correct, because we don't use P hat, okay? C and D are talking about, this is giving us basically our null and alternative being that P equals, which is good, because here we have our null being equal, so it could be either of these, but then what we want to look at is our alternative to decide what this is going to be. And if we look at this, basically the claim they're trying to make is that the correct percent is less than 45%, so our answer would be C in this case, because that's talking about less than. D would only be correct if we were saying that it's not equal to 45%. But we're talking about less than, so C is our answer. So good job, guys. All right. Okay, so which statement is correct about a p-value? So go ahead, read through these options, and let me know what you think. Awesome. Good job, guys. That's absolutely correct. So remember, we want to have a small p-value in order to make a claim that we do have some sort of statistical significance. Because remember, if our p-value is less than or equal to our alpha, we can claim statistical significance and say that we're going to reject our null. So we're saying that there's some sort of change. So in this case, so the smaller our p-value, the stronger evidence in favor of our alternative. So remember, our alternative is talking about there being some sort of change. So like we just talked about up here, if we do have that small p-value, then we're going to be able to reject our null and say if there's some sort of change, which is in favor of the alternative hypothesis. So A is correct. B isn't correct. It's saying the opposite thing. It's not in favor of our null, so that's not true. And then C and D aren't correct because they're talking about it being either or, which is not true in that case. So that's why A is the answer. So good job, guys. Okay. All right. A hypothesis test is done in which the alternative hypothesis states that more than 10% of a population is left-handed. The p-value for the test is calculated to be 0.25. Which statement is correct? Go ahead and read through these and let me know what you think. All right, good job, guys. Absolutely. So our answer is D here. So if we go ahead and look at this in terms of our p-value and significance level, so once again, we're going to assume here that our significance level is going to be 0.05 if we're not given it. And we're going to go ahead and see that our p-value is greater than our alpha because 0.25 is greater than 0.05. So we're going to fail to reject our null. So we are in favor of the null hypothesis here. So we're saying basically that we still think that there's no change. So in this case, we can't conclude that more than 10% of the population is left-handed. So once again, we are making this claim about the population, which is definitely important to remember. And since our p-value was greater than our null, we're unable to conclude. We can't conclude that more than 10%. Because remember, this more than 10% is talking about our alternative hypothesis. And we're going to fail to reject the null. So that's, if more than 10% was true, that would be in favor of the alternative. So in this case, we're not, we're going to not reject our null. So we're saying that we still think that there's no change. So D would be our correct answer. All these are incorrect because they're talking about can conclude something, which since our p-value was greater than our alpha, we're unable to conclude it. So D is our answer. Good job. All right, I think we have one more. All right, a team of medical researchers was examining the effectiveness of asthma treatments. They were comparing two treatments, old and new, and rejected the null hypothesis, concluding that their new treatment was superior. So which of the following is not a possibility in this case? So go ahead and read through these options. Let me know what you think. All right, great job. So yeah, definitely our answer is A here, because if we reject our null hypothesis here, then our two options are either going to be that we made a type 1 error, or we made a correct decision. So in this one, C-I-S-I-O-N, correct decision. So in this case, that's why we can cancel out B and C, because it says what's not a possibility. B and C are both possibilities. So A has to be our answer, because we cannot commit a type 2 error if we reject our null hypothesis. That's not an option, because remember, a type 2 error is going to be if we a false null hypothesis is not rejected. So that's why we're going to end up not being able to make a type 2 error if we did reject the null. So yeah, so good job. You guys definitely have a good grasp on that. All right, so that is all we got for tonight. Obviously, you can watch back this review as well as all the other ones on the YouTube channel with Stat with Anne-Marie. That's me. So you guys, if you haven't already given me your Penn State ID into the chat box or your email, please go ahead and type that in for me. And if you have any other questions, let me know. Our next review will be on Tuesday for our midterm. We'll start reviewing for the midterm then. And yes, I do have a Q&A on Wednesday till 1 a.m. So sounds like fun. So, but yeah, you guys are more than welcome to come to any of the sessions with any questions you have. If you have any other questions tonight, let me know. If not, you are good to go.